Hello everyone, my name's Logan and welcome back to the lecture hall. Today we're covering section 5.1, Areas and Distances. And this is the first episode of our UCI Math 2B Single Variable Calculus course. So, let's get right into it. As you will soon see, this whole course is about finding areas and eventually volumes, and then, well, some series and Taylor series and Maclaurin series, but we'll get there. But let's ask the simple question, how do we find the area under this curve y equals f of x? And what do I mean area? Well, I mean this whole blue section under the curve. And we could call this S. How do we find area S? Well, it's kind of a weird shape. Maybe it's a polynomial, maybe it's whatever. It's some sort of function. We know how to find areas of triangles and pentagons and rectangles, but we don't know how to find areas of non-symmetric shapes that just kind of have a curve and then a flat line. But this is where 2b comes in. And we can start with estimating our area. And how can we estimate our area? Well, if we want to estimate the area between, let's say, A and B, under a curve, we could split the graph into rectangles. What do you mean rectangles? Why rectangles? Well, rectangles are easy because we know how to calculate the area of a rectangle. It's base times height. So, what can we do? Well, we could split it off and we could use A as our left endpoint, and we could just try doing one rectangle across and B. And we say, wait, what is this area? Well, this area will be equal to B minus A for our width times, well, f of A, which is our height. But we see, well, that's kind of stupid. That's really stupid. There's this whole part of the graph right here there where it's not calculated, where the area isn't shown. Okay, well then what if we did one rectangle from the left endpoint, or the right endpoint, I should say, from B to A? Well, then we get this big rectangle, and we see, well, the area of this is going to be equal to B minus A, because the width is the same, times f of B. Okay, and why do I say f of B? Well, because that is the height, right? On the y-axis, that's the height. So we can say that's f of B. But we see, wow, this is a huge overestimation of our curve. There's just so much extra for our area. But what if we tried splitting it so that we made even more rectangles in our graph? Okay, well, let's do that. Let's say we made 4 rectangles. We can call this x1, x2, x3. Well, we can estimate our area, but first we have to choose, okay, we said we want 4 rectangles, but there's 5 endpoints here. And this is where that right and left endpoint comes in. You have to choose which height you want to be at. And you do that by choosing which endpoint you want to be at. So we can estimate with our left endpoints, and we go up to f of A, and we go across all the way to x1, and then so now x1, we go up to f of x1, go all the way across to x2. Now we go all the way up to f of x2, go draw our rectangle, and then finally we go up to f of x3 and draw our rectangle, and we see, well, this is our area, and in blue we see all the area that isn't part of our curve but should be, right? If we want to find the true area, it requires all of this blue, but it's not there. It's only these by these rectangles. Okay, let's do a similar example, but instead try with right endpoints. And how do we do that? Well, we go up to f of B, which is all the way up here, and we go over to x3. Okay, and then we do the same. At f of x3, we go over to x2, f of x2 go over to x1, and then f of x1, we go over to A and draw our rectangle. And we see, okay, well now this is definitely an overestimation. Because we see all this red, and it's like, well, this is way too much. The other one is way too little. What we should notice is, now that we have 4 rectangles, the overestimation and the underestimation is getting smaller. So, what if instead we did it with maybe even more rectangles? What would happen? Well, it should be pretty obvious by now that it would become less and less, because if we do this here, then we do the estimation there, go up, there, go up, there, and we see that, I'm not going to do the whole graph because that wastes too much time, but we can kind of see, like, okay, well now our underestimation is getting even smaller and smaller. So what you want to notice is, what if we took the limit of that? What if we increased our number of rectangles to n and we took the limit as n approaches infinity? Would that kind of maybe give us our exact area? And what we will soon see is yes. But we're going to get more into how do we calculate area with the rectangles and so on before we get to that. So I talked a lot about area and the number of rectangles, but we need to find out how to calculate the actual area of the rectangles. And I said it was length times width, right? Well, we know our length, right? That's just going to be wherever it hits on the y-axis. So if we were to draw a rectangle right here, then, and it went from here to here, well, this would be f of, let's just call that x. This would just be f of x, and that would be our height. But how do we find our width? And our width is going to be based off how many rectangles we have, right? Because if we have more and more rectangles, then our width is going to be decreasing. So how do we find our width? Well, we can call it delta x, right? It's the change in x. It's like, oh, are we changing this x by this much, or are we changing x by that much? Well, let's see. So delta x, and we're on the interval a to b. So we want to find, well, what is the length of the interval a to b? What's the length? Well, it's going to be b minus a, right? And then we want n rectangles. So our delta x should just be equal to b minus a over n. Okay, that's awesome. And then what we do with that information is we split our interval a to b into a bunch of sub-intervals. Don't worry about this right now. I'm going to talk about it in a sec. We split it into a bunch of sub-intervals. So a to b is actually going to be equal to a to a plus delta x, right? And why do I say a plus delta x? Well, because we're moving over delta x to our next rectangle, right? Our next line that we're drawing up. So this interval is going to be, and then union. And I put this union symbol because it's combining the intervals into multiple, right? So it's this interval, and the next one, and we'll have n intervals because we have n rectangles. So then, what's the second interval? Well, this is just going to be a plus delta x, a plus 2 times delta x. You're like, 2 times delta x? Why is that? Well, instead, because this is our second rectangle, we are moving 2 delta x's worth away from a. And we kind of keep going with this, and you can kind of see the trend. And what we do is we replace this a plus delta x with x naught, and then this is x1, and wait. Nope, this is definitely not. So this will be x1, our a will be x naught, so that will be x1, x2, and then this interval continues until we go from a to a plus n minus 1 delta x, comma, a plus n delta x. And we can rewrite these as x to the n minus 1, and then this is equal to x to the n, which is going to be equal to our b. right? And so this is how we break our intervals up into our widths, right? So this is how we get n amounts of widths. And now all you have to do is multiply it by the heights. And previously we talked about left endpoints and right endpoints. And so this is where we get a little function, not a function, an equation. We get this. We get that the left endpoint for n rectangles is going to be equal to f of x naught times delta x plus f of x1 times delta x plus dot 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 plus f of x n minus 1 times delta x, right? And that should make sense because you are taking the left interval, or the left endpoint, so it's always going to be x naught, x1, and then x2, and then all the way up to n minus 1. And now right hand is different. We use the other part of the interval. We use x1, so we get r to the n is equal to f of x1 times delta x plus f of x2 times delta x plus, dot dot dot, plus f of xn times delta x. And what that'll do is that'll give us a good approximation of our area with n rectangles. Now we get a definition. The area of the region S under the curve of the continuous function f is the limit of the sums of the areas of the approximating rectangles. Wow, that was a lot. But what does that mean? And what that's saying is the exact area under the curve is equal to the limit as n approaches infinity of Rn, which is also equal to the limit as n approaches infinity of Ln. So what is this saying? Well, we know our functions for Ln and Rn, we know our definitions, and what this is saying is as our difference, our dx, our delta x, is changing and getting smaller and smaller, well, as the number of rectangles goes to infinity, that will give us the exact area under the curve. So this is really cool, and we're going to use this to introduce integrals in the next video. So, real quick, we just have to go over the fact that we use sigma notation a lot. And we use this for when we're adding up infinite sums, or maybe not infinite, but where n is really large. We can't just take the time to write out first term, second term, third term, the infinity term, blah, 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 and so on. So what we do is we write this sigma notation. So we say R of n, or, well, L of n is a little different, but R of n is equal to the sum from I equals 1 to n of f of xi times delta x. And what does that mean? Well, it's just our definition of R of n, where it's f of x1 times delta x plus f of x2 times delta x plus dot 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 plus f of xn times delta x. So you're going to see this sigma notation quite a bit throughout this course, so just be pretty familiar with it. And yeah, now let's work on some distance problems, baby. So, distance is equal to velocity times time. And I know it's physics and it's scary because it's physics, but don't worry, I believe in you guys, you got this. So, this is really nice to compute when you have a constant velocity, right? It's really nice to just be able to say, oh, I was driving 25 miles an hour the whole time. But let's be honest, were you? No, that would be kind of impossible. You start at 0, and then you go up to 25, and then you put on some sweet-ass music, and then you hit 32 miles per hour in a school zone, and then you realize you gotta slow down. And your speed changes a lot, right? So it can be very hard to find our actual distance traveled, right? If we weren't to check our odometer, right? Well, what can we do? Well, if we measured our velocity in, well, right here we have it in lovely feet per second, but usually it's in miles per hour, but feet per second for convenience sake. If we were to measure our velocity every 5 seconds, we would be able to get a better reading, right? We could kind of estimate, kind of like we do with our rectangles. And you can kind of see the graph, our velocity change goes up, down, and so on. So we can do that with our rectangle. So at time 0, 25 feet per second. 5, 31, 10 seconds, 35 feet per second. 15, 43, 20, 47, 25, 45, 30, 41, and so on. You get it. So, how would we estimate it? Well, we do our right-hand endpoints and our left-hand endpoints, and we see, well, okay, how do we do it? Well, we just take this number, we multiply it by that, and we just go on and we count up all our areas, right? Because there are 1, 2, 3, 4, 5, 6, 7 endpoints, right? Or not endpoints, but times taken. So we're going to have 6 calculations in each one, and we multiply it. This is for our right. So we get 5 times 31 plus 35 times 5 plus 43 times 5 plus blah, blah, blah. We get, well, what do we get? We get 1310 feet per second, right? No, not feet per second, just feet. Because this is our distance traveled. And then we do our left, and we get it is equal to 5 times 25, blah, blah, blah. You know how to do it. We do 5 times this, and then 10 times this one, and then 15 times this one, and so on. And what do we get? We get our feet per second, or our feet is 1210. Okay, cool. So we get maybe an accurate reading, but it would probably be more accurate if we took our speedometer, we looked at our speedometer every 2 seconds, or every 1 second, or every 0.5 seconds. Wow, that was a weird jump cut. Well, if you're wondering, I gave a wrong explanation, and I didn't, want to have that in the video. So let's do the right explanation. And I guess the left explanation as well. Well, so we have that our left endpoint distance is equal to the sum from 1 to n of f of t I minus 1 times delta t. And we say, wait, hold up. T from I to f of t of I minus 1. Wait, I minus 1? Well, that is because, think back to our left-hand endpoint. We would use f of x naught, x0, times delta x when solving for our left-hand endpoints. And that's why this is f of t I minus 1, right? Because if we plug 1 in here, we get f of t0. Our right hand is the sum from 1 to n of f of t I times delta t, okay? And this should be similar, very consistent with our right-hand endpoint when solving for the area as well. And then what we can find is when we take the limit of both of these, we find that the limit as n approaches infinity of the sum from I equals 1 of f of t I minus 1 delta t. This is going to be equal to the limit as n approaches infinity from the sum of I equals 1 to n f of t I d delta t. And we will also be able to see that this will give us our actual distance traveled. So that is all for the lecture portion of the video. Let's transition into some practice problems. Alright, now let's do the practice problems. We're going to be doing just number 18. And that's because these problems tend to take a while, so we're just going to do one. The velocity of a car accelerating from rest to a speed of 120 feet per second is over a period of 30 seconds. Estimate the distance traveled. Okay, well, we know how to do this, but we kind of look at it, the graph, and I know it's kind of badly drawn because I'm not the greatest artist of all time, and, it's on a whiteboard, but we can choose how many rectangles we want to estimate with, and we can see, well, we can do it in periods of 10, right? So 10 seconds, 20 seconds, and 30 seconds, but that's not going to be very accurate. Maybe it will be pretty accurate for this one, right? From 20 to 30, there's not much increase, but from 0 to 10, they'll be way over. So we're going to do it in terms of 5-second intervals. And so what we'll do is the blue is the underestimate, and then the red is the overestimate. So we start at 0, right? F of 0, nothing. There's no triangle, right? And then if we start at 5 for the overestimate, we go over here, and then we do blue to 10, down. So then we get underestimate here. We get overestimate here. We do red, go to here. Here we get overestimate here. Right, and I'm doing both because we have to estimate, so we can just say, oh, it is in between this and this number. And also, this was, I believe, 120 kilometers per hour, but I just said 120 feet per second. I know that's not the proper conversion. I just didn't want to deal with fractions and stuff like that, so I'm just putting it in feet per second. So then we go from here over to 15 seconds. So then we have this underestimate, and then we go from here over. We have an overestimate here. And we just keep doing that, right? So we just draw over, underestimate, and then we just draw over. Okay. And then we draw this over and down. We draw this over and down. And then what do we get? Well, we do that over and down, over and down. And we get we can see our estimates, our over and under estimates are shrinking, right? And this kind of makes sense because our curve is flattening out, right? It's going, woo, and then it's flattening out, right? So how do we calculate this? Well, we know these are intervals of 5 seconds, so we have to do the left hand and the right hand sum. So we do left, well, what does that equal to? Well, it's going to be equal to f of 0, because that's f of a, f of 0 times 5. Well, that's just going to be 0 times 5, so that's nothing. Okay, well, then we do, what's here? So this is our dx is going to be, or our delta x is going to be 5 seconds, right? So then here instead we do, okay, where does it meet at 10 seconds? We do our at 5, and then we do f of 5 times 5, so that's 40. 40 times 5, okay? And then we just keep going along. Well, where is it here? Here it's at 80 times 5 plus 80 times 5. Okay. Well, now here it gets a little trickier. So we're done with that one, and that one. Now we go up, and then this looks like it's at 100. Okay, so then this is just 100 times 5. Okay. Okay, so then that one's done. And then, wait, is that 1, 2, 3, 4? Oh, we're not. Okay, we got to do this one still. So then we look at this one, and it's like a little more than 100, and because my graph isn't accurate, let's just call that 105, because that looks kind of like 105. So we'll say plus 105 times 5. Okay, and then here, it's a little higher. We got this one. We got this one. It's a little higher, and we see, well, kind of looks like 110. So we'll just say that's 110 times 5. Okay, now onto our right sum. And it's funny, I kind of... Now we're on to our overestimations. Okay, well, we go to 5, so we do f of x1 times delta x. Well, that's f of 5 times 5. Well, that goes all the way up to 40. So this is going to be 40 times 5. And what you're going to notice is the center terms, like this term, this term, this term, this term, and this term, will all be added here. And then we're going to add this final rectangle here where it goes from 120, right? And why do I say that? Well, that's because when we're doing our underestimations, we do it from the left-hand side, right? And then we do our overestimations, we're doing it from the right-hand side. And it's going just over, but they're the same measurements. We're just doing them at different intervals. So this is just going to be 40 times 5 plus 80 times 5 plus 100 times 5 plus 105 times 5 plus 110 times 5 plus, well, now we have to check this last rectangle, and we see, okay, well, this goes all the way up to 120, so right here, right? So it's right here, up, 120 and across, so we do plus 120 times 5. And so now there will be movie magic while I calculate it on my phone, and I'll give this interval. Poof. Movie magic. Well, so what do we get? When we calculate these out, that we get that the left-hand side, our underestimation in this case, is going to be approximate to 2,175 feet. Okay, and then we do our right-hand approximation, which will be our overestimation in this case, and we get, well, it was 2,775 feet. So that's kind of a big interval. So what we could have done is we could have split it into sections of 2.5 and whatnot, but that wasn't really possible for the purpose of this graph because it wasn't the most accurate graph. I was writing it on a whiteboard. But so what we can say is our estimated distance traveled is between 2175 feet and 2775 feet. Because the true distance traveled will be somewhere in that interval. So, that is all for the practice problems. I know this was a long first lecture. I hope you enjoyed it. Thank you for watching, and as always, my name is Logan. Have a great day.